Thanks for coming to this session. I'm competing with a bunch of other really great sessions at this time slot, so I appreciate you picking this one. I'll try and be as entertaining as I can. The topic is, as you've probably seen, LabVIEW Everywhere. You have to excuse me a bit. I had a couple of rough nights screaming at bars and things like that. I was singing last night to Mr. Brightside. And so let's hope my voice makes it through the whole presentation. But I may take a few water breaks during it. Please bear with me. Okay, so what was the kind of, why did I do this? And I guess about sometime in 2010, I attended an open day or an NI day in London. And I'm not sure if anyone there, you'll remember it. There was the guy from CERN was a keynote speaker. And this guy had a really bad day. Like literally his first day on the job, the accelerator broke. Like literally this 50 billion whatever instrument, just somebody had not welded something properly. That was his very first day of being the director of CERN. So that, like, if you think of you having a bad day, always think of that guy. But that was back on the era when NI was promoting their sort of grand engineering challenges, like problems that they wanted to help solve. Now I think that message has been a bit muddled or maybe lost over the last bit of time, but I thought it's a cool thing to think about. It would be interesting to look at the list if we had to see the grand engineering challenges if we did them again today, because I mean, who would have predicted vibe coding 15 years ago, right? I think one of the challenges is preventing that from getting out of control. With these engineering challenges, we all know, we're all LabVIEW users, probably somewhere in the pipeline, the innovation pipeline, you're going to find LabVIEW. Whether it's a scientist screwing around with, he's just got an idea, he wants to build something, maybe an entrepreneur, he's just got an idea. You get everything from that all the way to end-of-line production test and everything in the middle. And in fact, LabVIEW is even used for non-hardware based things. It's used everywhere. So I just wanted to show a few places where I've worked on it. It's just meant to be a fun, light thing. This is my journey. Everyone's journey is going to look completely different. But yeah, let's get into it. So quickly about me, my name is Neil Pate. I was born down at the bottom there. I'm from South Africa. And my accent's a bit weird because I've moved around a bit and I was screaming last night. I was born in Durban. I grew up there. It's best known for sharks and dolphins. The rugby team are called the Sharks. The cricket team are called the Dolphins. We have beaches and things like that. I grew up, I was educated there. I'm an electronic engineer, and my first job was at the Toyota manufacturing plant. There's a big one there, which is pretty cool. Like a car rolls off the assembly line every 45 seconds. So it's a cool place to start. But after a few months, I realized like these guys don't actually do anything. Like it's nice, it's cool, but there was no innovation. There was just Japan controlled everything. They told us how to make it. We just did it. So I got on an airplane, joined my friends in London, who were sending me messages about how great life was there, how much beer they were drinking, and so it wasn't too hard to sell. Currently, I stayed there for quite a while, about 15 years. Got married, had some kids. Moved back to South Africa with the thought that maybe my parents could help me take care of my kids. That didn't work out so well. For those who've been down that route, hopefully I'm going to be a better grandparent one day, but no. And then a few years ago, I moved from South Africa to the Netherlands, where I work now currently at Phillips. Phillips, I think, is a global name that everybody knows. And I'm in the test and verification department, which is part of a central engineering organization that provides services to other businesses within Phillips. So we're like an internal consultancy within Phillips. I got my CLA in about 2010, embedded developer, and in 2019 I was accepted into the Champions program. So I'm a LabVIEW champion, which just really means I like talking about LabVIEW a lot. So really, don't buy me a drink at a bar and ask me about LabVIEW. Like that's just unless you really want to talk about that kind of stuff. So onto the cool stuff. How it all started. That's a picture. Some of you might already have some ideas what's going on there. but the next bit should hopefully make it a bit clearer. I've got a soundbite to play. Hopefully this mic picks it up because it's going to play out my laptop speaker. So let's just try. So I think like 99% of the world will probably hate that sound, or maybe even 99.999 something. But the tiny percent that finds that cool, like that was me. That's obviously the sound of, I think we all know it's connecting to the internet back in the 80s or 90s, and the complicated thing that goes on with all the handshaking and signals. And it's all over the voice network. So everything, all the signaling's in band. The PSTN, which I believe at one point was classified as the world's largest machine. Or at least that's according to a book I had when I was 5 about trucks and machines and things. So I don't know how accurate that is. But obviously the PSTN was purely designed for voice communications. And only later on did we figure out, hey, maybe we can use this for data. But the trouble is they're stuck with that voice band. But this was my first introduction to LabVIEW. I just moved to London, and I hadn't taken very much money with me. I'm traveling from rands in South Africa to pounds in the UK. Your money goes very quickly when you're paying rent and buying beer in some order, right? And I wasn't very successful in my job hunt. And eventually I got a first interview. And at the interview they said, do you know LabVIEW? And I'd never even heard of it. But I was desperate. Like literally, they could have asked me, are you prepared to do this thing? And I would, yeah, I'll try. I'll do whatever. So they gave me a copy of the G168 ITU standard, which is the telecommunication standard for echo cancelling in networks. In a nutshell, what that is obviously when you talk on a phone, your voice goes to the other side, and probably a little bit of it makes its way back to you via the microphone on the other side. And that's pretty annoying, like to hear your own voice back in your head. So what the clever engineers did is they designed, convincingly enough, echo cancelers, which they put in line. And the whole purpose of that is to kind of measure the electrical signal, with DSP, try and figure out how best to remove the echo in real time. And you need to test that. So literally, that's how I started. This company made this device, which you can see on the right, the little box next to the laptop, called the DSP Genie. There was a few iterations of it before with the software done in Delphi. And I guess somebody from NI had convinced them to try a LabVIEW. And they did, but they needed a LabVIEW guy. And that was me. They hired me. And pretty much they said, we have to ship this thing in 6 months. And then my boss kind of looked at me and said, like, you have to ship this in 6 months, like implying that, well, if you don't get it done, that's it, you're out. Get back on your airplane and go back to your parents. So nice bit of pressure. Happily to say it all went well. I fell in love. I wouldn't say I fell in love with LabVIEW, but LabVIEW and I really clicked. Like my brain just thinks that way. Block diagrams, wires, data flow. It just really works for me. Unfortunately, I've lost pretty much. I didn't keep any of the original software I wrote, but I did find these pictures on one of the brochures. So this is modern controls. I mean, modern from the early 2000s. I think this is about 2004. This is basically the first bit of software that I wrote. Stupidly, one day I decided to change everything and implement it as a client-server architecture and all the dumb stuff you do, like when you're a bright-eyed engineer with just great ideas, but someone else's budgets. Yeah, things I wouldn't do now. This was a great introduction to LabVIEW, but also it was a pretty bad one because we were designing a custom DSP board. Inside that box is quite a fancy DSP card, which we had our own driver for. So I was new to LabVIEW, trying to interface with a new piece of hardware using DLLs. I mean, you can imagine I crashed LabVIEW thousands of times probably. And I think we were running Windows 2000, and I crashed Windows as well at the same time. Right? This wasn't just LabVIEW going down. This was everything. But, trial by fire, and if it doesn't kill you, I'm here, so makes you stronger. My first version of LabVIEW was LabVIEW 7, LabVIEW 7 Express, and actually, and a pure coincidence, in just the previous session we were in, Norma, the VP for marketing, was sitting in the back, and we started talking at the end of the session. And I didn't realize she was actually a developer at NI working on LabVIEW. And LabVIEW 7 was the last version she helped make. So I thought, oh, that's pretty cool. So I thought that's definitely worth mentioning. So I went from there and took a bit of a tangent, and I moved into the world of Formula One. This was England in about 2006. There weren't a whole bunch of LabVIEW programmers. I joined the team that used to be called Jordan. So Jordan was the yellow cars. They got bought out by this Russian outfit called Midland. I think that was all a bit of a tax dodge or something like that. Anyway, we weren't very successful, but it was Formula One. Who's going to turn down a Formula One job? I actually got the job effort was on the LabVIEW forum. They used to have a job category, and the guy just posted a job like saying, who wants to come work at a Formula One team? I'm like, I got on a train the next day, went for an interview, did a test. I managed to pass, and bam. So the top left photo was the view out of my office window, so I could see the cars in the bays as they're being assembled. So that was pretty cool. This was before phones with cameras, right? So I actually have very, very few, and I didn't own a digital camera at that point either. So I have very few actual pictures of any of the things that I did. But there is a bit of proof that I was there. The top right picture, you can see we're testing the front wing of the car. I was the test and calibration engineer, which meant I got involved in a lot of the actual manual testing, but also maintenance of the LabVIEW-based test equipment. In this instance, what I'm doing is, maybe can't see so well, but those are actually lead plates. So I'm manually adding lead plates to each side of the wing, and inside are a bunch of strain gauges. And I don't know if you can see so well, but there is a cable, and there would be a laptop with a CAN card in it, and we're capturing the strain was measured over the CAN because there was like a local communications module, and it was amazing because that was my introduction to the world of signals and sensors. Right, the previous job at the DSP company, that was just kind of LabVIEW and just bits and bytes on DLLs. But now I was really dealing with signals and calibrations and things like that. In the world of F1, every millisecond counts, right? I don't know any F1 fans here, but if you qualify ahead of the other guy, these days there's a good chance you're going to finish ahead of the other guy. And that was even similar back then. So the control systems engineers were convinced that we needed to measure everything down to like ridiculous accuracy. So we did, right? We had sensors, we had all these sensors on the cars. I mean, a modern F1 car has a crazy number of sensors. It measures everything from tire temperatures to pressures to the ride height to how much the car is rotating to how the gravity force or the triaxial acceleration in 3 dimensions. Position of the gearbox sensors, the gear that it's in. It's literally like I'm pretty sure some guy just sat down and said, "Let's just measure everything, and we can make the car go faster." And so we did that, and that was my job to maintain the test equipment, and that was actually one of the places where I started to do stupid things. So one of the dumbest things I did was I was about a week in on the job, and again, so new to sensors, new to calibration, and we had one of these sensors. I think it was measuring rotation on the car. So it's like a typical thing, calibration of say 5 volts per 300 per revolution. Right, and I was just trying to work out the maths, and it just wasn't working out. I spent a couple of hours thinking about this, and I had a number from the vendor saying this was the scaling factor, and I'd done my own maths, and I was getting a really similar number, but just different. So I eventually plucked up courage, and I walked up to my boss and I said, "Listen, I just don't get this. Like 5 volts, 365 degrees in a circle. Do the maths. It works out to this." And he says, "Say that again slowly." So I said, because I think now he doesn't understand, right? 5 volts, 365 degrees in a circle. And he says, no, just say the last bit again. I'm like, 365 degrees in a circle. And he's like, and at that point, I'm like, okay, I think I may have found my problem. Luckily, they didn't find me on the spot for being an idiot. Like that's I was still in my probation period, so that's kind of something they could have done. I did nearly get fired later on because we had some LabVIEW-based test equipment for measuring pressure sensors. So we used, again, let's measure brake pressure, let's measure all these kind of things. So we had some very expensive pressure sensors that were in short supply. I mean, F1's like aerospace, right? You go to a vendor, they hear you're from an aerospace or F1 company, they just add an extra zero to the quote, right? And they're probably giving you the same thing, and they're just saying, mill grade. But we were a very small team compared to modern F1 teams. Our budget was like 100 million euros a year, whereas at the time Toyota was spending, I think, 1 or 2 billion euros a year on the F1 team. And we had these pressure sensors and connected them to the LabVIEW ATE, but I had mixed the sensors up. So we have brake lines on the car which are running at like 100 bar, and then you have other lines on the car which are running at like 4 bar. And I'd programmed it wrong in the software, and I accidentally ran the 100 bar profile on the 4 bar sensor. And just by some miracle, my technician caught it at the last second before the test actually run, because we would have burst the sensors. If you don't have sensors, you can't measure these things, and the car probably wouldn't have raced in a race. Like we just didn't have spare parts, and there I think I would have got a proper talking to. So thankfully that wasn't too bad. It's also where I started to blow things up. Like for some strange reason on an F1 car, you have things that run at 12 volts and things that run at 5 volts. And well, in those days, it's the same connector. So I definitely let the smoke out of a few devices a few times. And again, like these were not cheap mistakes. So from F1, fast forward a few years, that's when I left permanent employment, and I decided to become a LabVIEW freelance, or contractor, effectively. And that was the best decision ever, actually. F1 was good, but the team I was in, they were losing. Strangely, the moment I left, they actually started to start winning again. So I'm not going to make any correlation, but they did better once I left. But when I became a freelance is when I then I really got exposed to a lot of different things. Like, I don't know if there's any other freelance or contractors in the room, but that's when your knowledge really builds. So one of the cool things I got to work on was this chip you can see. So on the left-hand side is a PCBA, and the chip is the thing on the right with the yellow border. And it's actually designed by CERN, and it's called the Medipix chip, and it's effectively just a camera. It's a camera for things like gamma rays and X-rays, and it can be used in particle accelerators. They can use it for crystallography, for measuring all sorts of things. And we built a LabVIEW-based test system to interface with this thing. And it was my first exposure to LabVIEW FPGA with the clip node. You know, like you get the clip which you can attach to it. The problem when you have a clip node is in your FPGA code, you end up having to talk about the clip clock. And one day the code was running slowly and somebody made a joke about a donkey. And from that point on, whenever we would say clip clock, it's almost impossible to not think about this donkey slowly walking along the street. So luckily I don't do any more of that stuff. Also, I hate VHDL. I really didn't get on well with this. So no more clip clocks for me, thankfully. I did also screw up this project because towards the end I was asked to implement some kind of communications bus. I forget whether it was an SP I bus or I2C. And I did this nice fancy state machine, and it just didn't work. Well, the first thing is the compile times went from like 10 minutes, which wasn't too bad on FPGA, to like something like 2 hours. And all I'd done is implemented a state machine. And at that point, actually, I don't remember if I was kicked off the project or just asked not to come back, maybe because they'd run out of money or something like that. And it was only much later that I realized that in my state machine, I actually had included the error cluster just to sequence everything through. And it's actually compiled and worked. And it's surprisingly, LabVIEW didn't seem to moan at me. But I think what happened is the string in the description was just causing the FPGA code to generate all the string handling unnecessarily. And I didn't need, I was just like so used to our state machine, put the error cluster through, never really thought about it. So yeah, don't do that. So while we're talking about fast things, let's talk about even faster. And I think we've heard NI enough times, this NI Connect talking about the vector signal transceiver. And I had the pleasure of working with one. The VST, for those that don't know, is an RF device. It can output signals. It can measure them at the same time. It's super powerful. Like it's basically FPGA based. You can see the size. It's a big thing. It's super expensive, right? Like you can almost buy a small apartment for what you would pay for a VST like this. This is one of those projects, unfortunately, I can't go into too many details about. There'll be a few like this because I'm under a bit of NDA. This one was used by, let's just say, shady governments trying to intercept satellite signals and decrypt effectively the traffic on them. I'm not going to mention the governments. I'm not going to say anything about it. But there was a company that I worked for would sell the service to governments around the world, and they would just be able to deploy the system anywhere. And effectively, because the satellite signal is being broadcast, anyone can listen to it. The securities and the encryption. And the trouble is a lot of the satellite stuff, and these days you can just break it, right? It's old. Like it's sometimes 20-year-old birds flying in the sky. It's just old stuff. But that was a super cool project. The only problem was I wasn't anywhere near the machine. I had actually taken on another role in Denmark. This system was based in South Africa, so I had to do all the development and debugging over a remote desktop, which from 10,000 kilometers away was just a hideous experience. Also coupled to the fact of that one is that we really had to try and squeeze every ounce of performance out of the PC because we were running at 120 megahertz bandwidth with INQ channels, and we're trying to stream to disk and potentially play back. Like it's just a lot is going on in the PC. So I used user events a lot because that's how I design my actors. The trouble with that is actually it's very easy to get an out of memory situation where you just get a dialog box popping up on your screen and that's it, boom. Like you have to just stop. And when you're trying to do any kind of streaming thing, you can't put a probe on, you can't put a breakpoint because all of a sudden your generator is still generating code, and you typically get out of memory errors that way. I think I probably could have been a bit smart about it. Had I thought about it, I probably could have baked that into the generation side, like some kind of debugging mode where I maybe slow down the data generation. I didn't, but it was a pretty cool thing to work on. This was actually also my first exposure to the eDVR. I don't know if anyone's heard of it. I only know what DVRs are, right? The data value reference in LabVIEW, which is like a pointer. Anyone used an eDVR? Okay. So I'd never even heard about these things, but they're pretty cool. And what it effectively allows you to do, and I might get some of the details wrong on this because it was a few years ago, but in your FPGA code, you can effectively take, obviously you're using DMA transfers to get all the data because there's no way you could do it otherwise. But you can effectively configure, you can have a TDMS file, which has an input, and again, I might get the directions wrong, but you effectively are able to link a TDMS file with your FIFO, and magic just happens. Like things, it just somehow gets off the FPGA. You don't even have to read the data directly in the host PC. It just happens, and it ends up in the file. I guess somewhere on some low-level driver is taking care of it. That was pretty cool. Unfortunately, I couldn't use that mechanism because they said to me, we'd also like you to log it as raw binary data. You can't use TDMS. So I got super excited that this thing was going to solve world peace, and then I couldn't actually use it. So cool, but not usable. So one thing I forgot to mention is on the right, you can actually see like a network attached storage device. And we had to effectively record sessions for potentially days and days running at a time. Because like when you deploy this thing to the field, you don't know when the bad guy's going to send the message, right? So you just have to be listening all the time. the data rates are crazy. I think it's up to something like a gigabyte or so per second that you just continuously have to stream to disk for potentially days at a time. So we had this giant SSD-based NAS running in RAID, where you do the striping or whatever to get the maximum performance out of it. And when it worked, it was pretty impressive, right? We were really able to get something pretty cool out of it. This was before the days of Instrument Studio and things like that. So I think we may have done it differently if we had the modern tools. But we did bake in some pretty cool visualizations, kind of like the one you saw in the first few slides with the dial-up sequence, where you got a frequency diagram, and there's I'm not an RF guy, so I just kind of followed the instructions of what visualizations they wanted to do. But we did some pretty cool real-time displays of the signal, so somebody could watch it and see that a signal was coming in. So now from fast to something slow. Those silver boxes that you see there are ovens. And this was a project that I helped for Imperial College London materials laboratory. There's probably a better word for that, but I don't think I can say it. It's like metallurgical or something, but material science. And effectively what they do there is they test the formulation of new materials that they're making. So the students or postgrads come up with new compounds, and they do some kind of accelerated life testing by attaching the samples, heating them up, and then stressing them. So I don't know if you can see, but I don't know, is my mouse showing? No, it's not. But at the bottom, you might not see it so well, are actually just some weights. So they're able to weight down a sample. The sample is like a piece of metal like this, and they clamp it, and they pull it with the weights, and then they chuck it in an oven, and they heat it up to like 500 degrees, and then they leave it for 6 months. Because that's how long it takes to fail, right? Potentially, like if it's a good one. If it's a bad one, it might fail much sooner. So we developed this pretty cool long-term, but very slow. It's a very, very slow process. So like if you think about the VST, we were running at 120 megahertz bandwidth. This thing's running at one sample every 5 minutes because the thing's just not moving. So we could measure the elongation of the sample and also temperature. And this was all done by multiple compact RIOs, which were then marshaled by a central PC. This project was fun, but also less fun in that debugging I did over remote desktop. I don't know why I do this. Remote desktop debugging is never fun. I actually lived in London at the time, but rather than get on the train and go into central London, it was easier to just remote in. The issue is that the PC I was remoting into was also the lab PC that the students were using. So I'd be in the middle of a debug session and somebody would just log me out because they had physical access. The way I eventually solved that was I changed the background of the Windows desktop to some big text saying, if you keep on screwing with me, I'm going to delete all your data. That actually seemed to work. So now something completely different, rowing. I'm not a rower. I know almost nothing about rowing, but I know a little bit more now that I've done this project. And that's an interesting side note. And that's probably one of the coolest parts about our job. It's like if you work on something, at the beginning of the project, you know nothing, right? Like it's a new domain, it's a new everything. You know about LabVIEW, maybe you know about measurements, but you don't know about the Dutch, you don't know about the system, you don't know about the science, you don't know about anything. And at the end, actually, you know quite a bit. You can have a sensible conversation with someone, and you can even start correcting them on things like, no, I think we should do it that way rather because X, Y, and Z. And for me, that's just such an incredible benefit of the work we get to do. It's very satisfying to be able to continuously learn. So I helped the Great Britain rowing team, the Olympic rowing team, with some instrumentation for their boats. Actually, coincidentally, at Phillips this year, at the beginning of the year, every year we have a town hall where they get like a celebrity, and we had one of the rowers in from the Olympic team from the early 2000s, and their motto was, will this make the boat go faster? Like literally every single decision that they did was, you had to answer that question. And if the answer was no, then they didn't do it. Like, interestingly, none of them attended the opening ceremony because it would have meant they would have had to stand for 4 hours and they would have missed 2 meals. So there's a picture of them all sitting on these crappy plastic wooden chairs, watching the opening ceremony of the thing they've waited their whole life for, but that little bit, the peak performance that they just didn't get. So again, like, I don't know much about rowing, but on the bottom right is a curve of the stroke of rowing. I don't know if anyone at the gym's ever got on the rower, but basically you sit and you pull the handles and you do some things. And there's 3 phases. There's the catch, the drive, and finish. I don't know what order like a rower could probably tell this much better, but you can get data if you do instrumentation on your boat. And what they do is actually on the oar lock, which is the thing that's, if you think about a rower, you've got the oar in your hand, and somehow it has to pivot before it, if you didn't have anything, it would just wouldn't work. So the oar lock is the thing, you might be able to see it, where the oar goes through and attaches to the boat. And you could put instrumentation on there, measuring all things like rotation and force and time. And they would have an embedded data logger on the boat. And they were able to record the performance effectively of all the athletes on the boat. And then we made a system in LabVIEW that was able to extract the data off this data logger and then do all kind of cool analysis, like comparison of how different teammates were doing. Like maybe on Monday, his performance was better than on Tuesday, or teammate A was doing better than teammate B. I mean, this is Olympics, right? It's a sports scientist day. It's a serious game. If you don't do this stuff, the other guys who are doing it are gonna beat you. And by the time you're up at that level of trying to win Olympic gold, you'll do everything you can. I had a really interesting experience with this project because I thought I'd done a pretty good job, right? We made a lovely LabVIEW GUI. It all worked nicely. And I was doing kind of one of the final presentations to the customer. And he said to me, Neil, I just want to show you something that I've done. And we'd been sharing the code with them, throughout the developments. And he said, I rewrote your GUI for you. And this was a sports scientist he'd never done any LabVIEW before. So here's me, consultant, I don't think I was an architect at that point, but I thought I was reasonably hotshot. And he told me I found out about X controls. And he'd taken my whole GUI and rewritten it as a single X control and miraculously managed to get it to work. Like, I can't imagine the amount of frustration and pain he had to go through for that experience. But we had a good laugh and we agreed never to speak about that again. And the X control implementation didn't make it in. I think he stuck to sports science because that was the thing he was good at. He was just curious on the side. Now onto something that I probably would do without even asking for money for, and that's working in space, right? I love space. I've always been fascinated by rockets and everything like that. So I got the opportunity to work on a piece of test equipment for testing the mechanism on the left. So the thing on the left is the DUT. It's called an ADTM, and it's an ADTM Mark II. And what an ADTM is, it's an antenna deployment and trimming mechanism. So this thing attaches to a satellite and effectively is used to control the antenna. So when the satellite is launched, you don't really want your antenna in its normal operating position because it's probably going to fall off as it gets shot into space. You have it nicely tucked away in a little protective space. But when you get to space, you need to position it. And interestingly, I said this was the Mark II. In the Mark I, they had a really interesting way of doing the initial deployment. And so that the initial deployment is when it's going from its storage position to some kind of nominal in the middle. Okay, let's start now. And the way they did on the Mark I was they actually used a pre-coiled spring, so a tightly coiled spring with an explosive charge that they would effectively just blow up in space, which would then uncoil and effectively rotate the antenna into position. I mean, I thought, wow, that's an interesting way of doing it. I didn't question it. But this was the Mark II, where they decided to move everything to electrically actuated. So it has a bunch of stepper motors, and they use stepper motors to do the deployment as well as the trimming. Why do you need to trim the antenna? Like what is trimming? Like these satellites typically are in geostationary orbit, so they're parked up in a certain place, and they stay there forever. In theory they do, but actually, of course, I don't know which one of Newton's laws it is, but it says that things are going to keep moving. Like there's always going to be a tiny little force. So the satellites in space will drift around a little bit, right? That's just the way things are. And so they have thrusters on board the satellites to correct position. But you don't want to be you don't want to be firing off your thrusters every time a little bit of drift happens. Because if the satellite's meant to last for 10 or 20 years, you've got to have propellant on the satellite for 10 or 20 years worth. So what they actually do is they allow the satellite to drift around in a box a little bit, so a box in space. And while it's drifting, they electrically are able to reposition the antenna so that it's pointing to the same place on Earth. Obviously, they have solar panels, so that electricity is free. They have a free supply of it. And only when the satellite drifts to the edge of the box, or I guess it's a cube, a space, not a plane, do they then use thrusters to reposition the satellites back to the middle. Something like that. So we made a LabVIEW-based test equipment for the device, and it was actually used for design verification as well as production testing. So the thing in the middle that I'm snuggling up to is a ground support equipment. So I think it was mentioned in one of the other, maybe it was yesterday in the keynote. It's I called it an EXI, which I didn't. That's what it was called. It was an electrical ground support equipment, where effectively you can plug in your DUT and command stuff with it. So it's a stepper motors. So we had some quite fancy FPGA control to make the steppers turn as you want them to turn. And they're obviously in space, everything needs redundancy. So there's multiple sets of windings on the motors that if one winding fails, maybe due to some kind of thermal cycling in space, obviously it gets hot and then it gets cold, then it gets hot again. So our test equipment was able to switch between those windings. Interestingly, again, those of you who are eagle-eyed may have spotted these connectors on the bottom left, or on the left-hand side, with the red caps on them. And they're actually just regular, I would say regular, it's aerospace, but they're just sub-miniature D-type connectors. And I was a bit shocked to find out. So I'd come from Formula One, where we use like super high performance connectors, because I guess there's a whole bunch of vibration and stuff like that. And I said to the guys, like, why do you use D-types? And they said, because we've been using D-type for 50 years. And they have no reason to change it. And I don't know if they still use D-types. This is from about 15 years ago now, so maybe they've got a slightly more advanced technology. But I thought that was pretty cool. What they do actually do, though, is they have a sacrificial connector. So when the device is integrated onto the rocket or integrated into its final assembly, they only ever, I think, are supposed to make that connection once. They literally plug it in once, and they're not allowed to unplug it ever again. Because obviously D-type's not great at constant mating and disconnecting. It's just not designed to do that. So while you're doing all the other testing down on Earth, you have this sacrificial connector in the middle where you can connect to, which eventually you end up throwing away when it comes time to final integration. This was a great project. It was actually my first exposure to LabVIEW FPGA. And the fantastic compile times that come with it. I was used to, like, you build and you run and you're off and you're done. But we had maybe, I guess it was my first FPGA code, so I probably didn't write it as well as it could be. But it was taking about 45 minutes or so to compile the code, which I believe is actually that's not bad by some standards. But one day they asked for a feature, or I forget what, I was implementing some kind of feature, and I wasn't fully in the game. My mind was on something else, and that the next day I was going away on a short vacation. I was traveling to Wales to go watch some cricket. So the Ashes, this is England playing Australia at cricket. I don't know if cricket is a thing you guys are too familiar with. It's team goes in and then they try to get you, the team that's out tries to get them back in. It's like baseball, just with more people, and it's a weird thing. But anyway, it's really just an excuse to drink beer and sit in the sun. And you can do this for 5 days. It's fantastic. So I made the change to the software, and I waited for the build to finish, and the build did finally finish. But I had to get home and I had to go to bed because I had to be up early the next day to go to Wales. So I didn't test it. And everything was fine until about halfway through the next day. And I was well on my way through my liquid lunch when I got a phone call from the manager. And I think he just said, "Neil, it's a disaster." And I'm like, what's happened now? And one thing I haven't mentioned is all the initial testing. And this is a bad idea. I can't actually recommend it, but this is what they did. We only had one device, the golden sample, the thing they were going to use for design and verification. There was only one of it, and we had to use that to build our software. So we had to kind of bring it up at the same time. And when you put something in space, you want to make it as light as possible. And so what they actually do on these devices is, obviously when something's rotating, you typically have some way of mechanically stopping it from over-rotating. Like if this was an Earth-based system, you would put another block of metal so that at some point it just can't rotate anymore. Well, they don't do that on satellites. They instead trust that you just write good software. Well, I didn't write good software, and I managed to get this thing to rotate all the way around, and it just didn't stop when it should have, and the springs fell off and the whole thing fell apart. And I set back their testing program by some unspecified amount of time. But they took it quite well. I definitely learned from that. Never factored that in. Testing is important. And I'd love to say that was the last time I made a big mistake. Unfortunately, that's also not true. But it's the last time I made a mistake for those guys. On to more space stuff. Right. On the left is a big mirror. So that you can see the people there. It's about 2.5 meters in diameter, and it gets integrated into the thing on the right, which is a giant Earth-based telescope for space observation. This is now currently sitting somewhere in a desert region of India where there's no rain and no pollution and no light pollution or any kind of pollution. And it is currently working, so I'm glad to say that I didn't break this one. But this thing has some super cool engineering in it. You can see how big that thing is, right? On the right-hand side, there's a guy. That's not me. That's one of the other engineers. But it's a pretty big thing. And the cool thing about this project was the active optics system that we developed. So my involvement was we had a LabVIEW GUI, which was effectively the operator GUI for the whole telescope that did all the sensible things that you would do on a telescope. But it also implemented the control system of the active optics. And that's the cool bit, is we used a thing called a wavefront sensor, which effectively, again, is also just like a camera. And what you can do is you can look at a distant star and treat it as a point light source. So effectively, it's so far away that by the time the beams get to you, you consider them to be not much gets you perfectly parallel or something like that. And any distortion in the atmosphere will cause the beam to split a bit. And with a sensor enough a camera, you can see the pixels have diverged a bit. So we actually used this to do real-time control and correction of the image. So the bottom left picture is the mechanism that the mirror is mounted on top of. And those funny metal things are pneumatic actuators, which push upwards. So the mirror rests on top of it, and I think there were 65 of them, individually controlled. And by gently, and I really do mean quite gently, in the order of single newtons sometimes, pushing up on this mirror, which probably weighs a couple of tons, you're able to ever so gracefully modify the profile of the mirror to correct for the disturbances you've detected in the atmosphere. And it's pretty cool. It's happening in real time at about 1 hertz. So you have this active deformation of the mirror. Some really fancy maths behind it. The company that does this employs optical engineers who it's just a whole different world of, I have glasses, I can't see, so I understand things like focus. But then you've probably heard of things like astigmatism. And there's all these other modes of failure, or that you get, or not failure, but just modes of distortion in an optical system. And between the optical guy and the control systems guy, they came up with algorithms which they modeled in MATLAB, which they then just, thankfully, like they would give me working MATLAB code, which I could then translate into LabVIEW. There's no way I could come up with any of that stuff. But I tried to get a picture. This telescope's performing really well, and there's some really nice pictures out there. I'll see if I can find some. Guys, I'm taking much longer than I expected, so let me be selective on the slides. No more space stuff. I didn't break anything on this project. Let's talk about this one. Okay, so I currently work for Phillips, so it's probably fair that I speak a bit about how LabVIEW is used within Phillips. Phillips is a giant company. We have test equipment everywhere, from some of it's 30 years old, some of it's still being built. Like we have everything. But I want to tell you about some of the products that we make and how LabVIEW is used in it. So the picture you see on the left is like a suite of products that maybe anyone who's ever had an X-ray might recognize some of the stuff. Effectively, you generate an X-ray, you generate an X-ray, you shoot it through a person, you detect it somehow, and you can see what's going on in your body. Right? That's the basic principle. I think who was it? Röntgen, I forget who it was. Him and Madame Curie figured this out some time ago, and it's being slowly refined. The problem with X-rays is we know how to make them, but we can't really make them in a nice controllable manner. So like you just burst out a whole bunch of them. You apply a high voltage, something like 50, 60 kilovolts. You have an anode, which is typically kind of it might be a cathode, which you heat up and you spin, and then electrons fly off, and that somehow makes X-rays. Like I'm definitely not an expert. The bit I do know about is the thing that you attach to the X-ray generator to make it more usable, and that's called a collimator. So on the right-hand side, you can see that thing is a device which is kind of used to focus and to form the beam of X-rays into something that's usable. So imagine you're lying on the table. You can see there you're obviously doing nothing. You're just lying there. But the medical professional has to position the X-rays in such a way that they take a picture of the right place in your body, right? So they use the handles, and everything's nicely motorized, so you can grab those handles and you can like almost frictionally move the device to the right place. But in between the handles is that square box, and that's the thing that I'm showing on the right-hand side, but that's kind of a view from the bottom. So you can't see it so well, but inside, oops, I shouldn't have done that. Inside the collimator is a bunch of LED shutters, which can shut in this direction and this direction to effectively block the X-ray, but also to then to refine it to exactly the position on the body you want to. And they also have effectively filters built into the collimator, which is a way to reduce the X-ray radiation going into you. You don't always want the full dose that the X-ray tube is giving you. Like the source of the X-ray generator is, as I said, it's not nicely controllable. You've got to control what actually comes to you in another way. And the way you do that is with these filters, which are basically aluminum discs. They use aluminum discs of different thickness, which we can rotate in front of the beam to effectively attenuate the X-ray. You'll be pleased to know none of this is powered by LabVIEW. Like none of the systems that are in hospital, LabVIEW's nowhere in the actual product. It's all Linux based. It's all embedded. It's not LabVIEW based. But we use LabVIEW everywhere else. So from design verification all the way through to final production testing. And for a collimator, quite a bit of testing has to get done. So one of the first things we do is we check that the shutters are moving nicely, and we can do that by measuring the motor currents. We then can check whether, if we say it's going to go to a certain position, that it does. And the way we do that is by using a light source. So we have a second piece of test equipment that effectively mimics an X-ray source with a source of light, and you shoot it through the collimator, and effectively it forms a cone or a beam, and then you have a detector at the top with the camera looking down, and as your shutters change position, so that the shape of your light changes. So we have that, and then in the final system, it's all put together. In principle, when everything's nice and tight and closed up, there shouldn't be any leakage, right? Like you don't want X-rays to be leaking out of your system anyway. So we do leakage testing at the end before it's shipped out, and that is all LabVIEW controlled. Okay, I'm gonna skip this one because this one's a bit cooler. So, aerospace, right? Defense. It's, again, very commonly used in LabVIEW. There's probably people in this room who actively work in defense. I was just parachuted in for this project and asked to help out a little bit. But effectively for this project, and again, this is one of the ones that's definitely under NDA. If I say too much, government officials are going to knock on my door at the hotel later. So I'm not going to mention any names or places. All of this information is pretty much commonly known anyway, so I'm not going to give away any secrets, but you might not know it, and I think it's pretty cool to share. So if you have good guys and bad guys, right, and that's always relative, well, who's the good guy and who's the bad guy, and one of them is trying to shoot you with an airplane of some sort, well, you don't really want him to shoot him, you want to shoot him first. And the way they do that is typically with the missile, and you shoot. And the missile, and the thing on the left is an AIM-9. I think it's commonly called a Sidewinder. I think it's a surface-to-air or air-to-air missile. I don't know too many details. But essentially, in the nose of the missile is an infrared camera. So it's used to, just before you shoot the missile off, the operator, maybe it's the fighter pilot or a guy on the ground controlling it, somehow determines a heat source and says, follow that thing. And that's really what it does. So the infrared detector on the front of the missile controls the fins, controls the guidance, and the missile hopefully then shoots off at whatever Mach 4, I don't know how fast missiles go, I think it's pretty fast. And from their perspective, hopefully hits the thing it's trying to hit, right? Okay, I'm going to get my good guys and bad guys mixed up, so it's probably a bad analogy. The other guys probably don't want to be shot down, right? And they know that you're going to try and shoot them down. So they've developed countermeasures. And you would have seen these in action. I thought that's a pretty cool picture I found. That is I think it's a Hercules or something, deploying flares, which effectively is something really hot that's hopefully going to confuse the heat-seeking missile. That's the idea. It's like just put so much crap out there that it's hopefully going to then rather go that way. And we've all seen Top Gun and stuff like that, where this all works. And I thought that was a pretty cool picture. But the guys who make the missile know that these guys are going to do that, right? So they then have to write software that tries to figure out what to do in the event of this countermeasure. And that's the cool system I got to work on, was actually essentially an optical test bench where the DUT was that front piece of the missile, so the infrared detector placed on a table, and then we had a heat source, which was effectively like a really hot lamp in like a black box controlling, enclosing it, and then a series of mirrors that were powered by motors that we could essentially show the DUT or the missile a heat profile of a target. So like different planes have known targets, like the F-14, I guess it's got those two iconic tails that glow bright. This Hercules has probably got a different heat profile. And effectively, optically, we're able to recreate those patterns. And then we're able to introduce a pattern of a countermeasure. So we could optically overlay what it would look like if that heat source also had some countermeasure active. So, for example, this Hercules, and obviously the chaff or the flares, they start out there, but then they go out over time. So over time, we're able to to replay effectively. It's almost like hardware in the loop system for the missile. And that's what Albert did. And then another team of software engineers working for the other defense contractor, they then wrote the algorithms to try and make the missile better at sticking to its original target, right? And not going off and accidentally shooting our stuff. This was actually controlled by a PC running Linux RT. So it was, I think it might still have been FarLab days, or I don't remember too many details, but it was my first exposure to, I didn't even know you could put RT on a PC, but sure enough, that's what happened. Okay, I've got 4 more minutes, so I'm gonna skip over this one because the next slide's important to me. That's me with my first child, and parents in this room. I mean, we've done this, right? That's me feeding my daughter, and I used, little did I know at the time, I bought the Phillips Avent system for feeding. And ironically enough, when I joined Phillips 14 years later, one of the pieces of software I worked on was a piece of software that's used to characterize the breast pumps that we make. And it was super weird. Like, I don't know, I mean, for those who've done it, the noise of a breast pump is something you kind of never forget. It makes this really distinctive thing. And I had forgotten it. And then one day I was in the lab with the software and we started the pump up, and just all these memories of came flooding back of my kid and the hours. I mean, as a parent, you spend hours trying to get your child to eat and to sleep and to shut up and to, but they're great. Like it's stuff that you just miss so much. And I thought it was really kind of like such a nice coincidence that years later I got to work on the same system. And nothing got broken in this one. I just thought it's a really cool way to kind of wrap this up. I've got a few other slides of other stuff where LabVIEW is used, but I think we're kind of out of time. I don't want to go too much, and I don't think my voice is going to last too much longer either. I just thought maybe I'd end off with, you guys must also have done some cool stuff. Does anyone have a story to share of something like super out of the ordinary, a place they've used LabVIEW that they can share with us? One thing I forgot to mention is I'm hoping to take this presentation and sort of tailor it to school kids. So kids who are getting into STEM, like high schoolers or kids who are kind of figuring out what they want to do with their life. Because like my kids are getting to the age where they're starting to make these decisions. I don't think either of them are going to go into that field, but I'm still, if I can just recruit one more engineer, then I've done my bit. So anybody, any stories that you can share? We actually are pretty much out of time. So if we don't have any, that also works. But cool. Well, thank you so much for entertaining me. I had a good time.